Okay, so let me start the introduction by telling you about the model in which we operate. So it's a very hands-off model. In a way, you could even say adversarial. So I'm going to imagine that I have access to a device, and I'll model this device as a black box. So this is a device. And this device may be quantum or not, I don't really know. The way I interact with it is by providing inputs and collecting outputs. So there's a way here to provide instructions. So this is the in channel. So these instructions, I can call them inputs. Okay, also here, I'll try not to use the bottom too much because I know at the back it's hard. So you can call them input, or you can call them questions, because we think that we're executing some kind of a test with this device. Then the device runs for some amount of time, and it produces an output. So this output, I can think of it as outcomes or answers to my questions. So I'll give more detailed examples later, but just let you understand the flavor, the kind of inputs that I could give. They'll always be written in English. I mean, they're the classical inputs, so they could be, please factor this large number for me, okay? And then the output will be some numbers. The input could be, please evolve this Hamiltonian for time t, and then measure, some observable of the resulting state, and the outcome will be some sequence of digits. But it's a black box approach because we don't want to make assumptions a priori about what's going on inside the box. Okay, my model is just that this is a box. I can provide inputs. I provide, and it provides outputs. And so, what are our goal? So the goal is written on the board here, is to design a family of tests such that two main properties hold. So first of all, what do I mean by test? So what's a test? A test needs to specify two things. It needs to specify how the inputs are generated. So ideally, there'll be some algorithmic procedure that says how I generate this. For example, choose two primes at random and multiply them to generate the input that we'll fill in. Okay, that's an example of a description of an input generating procedure. That's one thing. And then the other is that there should also be a verification procedure that takes the output and then performs some kind of calculation and validates it or invalidates it. Okay, the verification procedure is going to decide whether the outputs are valid or not. For example, it expects two numbers, and it's just going to check that neither of them is equal to 1, and their product is equal to the input number. Okay? And in that case, I'll say yes, correct, and otherwise I would say no. Okay, so to specify a test, we need to specify how the inputs are generated and how the outputs are validated or not. And we'd like to design tests that have two main properties. The first one is usually called completeness, and the other one is called soundness. The completeness is that I want there to be some device that succeeds in my test. I want to explain this a little bit more because both the completeness and the soundness come in two different flavors. There's okay, so let me put it here, completeness. Concrete completeness, so by easy for honest quantum device, it means that there should exist some implementation of my test that I can run right now in the lab, or let's say within the next couple of years, and it's going to succeed in that test. So there exists an implementation now. Okay, and the soundness states that it should be impossible for any classical device to succeed in my test. So concrete soundness would be, well, at the moment, given whatever supercomputer, classical supercomputer I have access to, I'm not managing to implement a procedure that, given the inputs, generates outputs that succeed in a test, except with negligible probability of success. So currently, cannot succeed in the test by using a classical device. Okay, so that's concrete completeness and soundness. The symptotic completeness and soundness look a little bit further in the future, and they ask about the scaling of the complexity of realizing a quantum device, respectively a classical device that succeed in the test. So in order for this to make sense, we need to have not a single test, which is like a finite object, but we need a family of tests. So in this case, we'll have a family of tests, and they're parameterized by some integer, or maybe k, let's say. K would be, loosely speaking, a parameter that describes the complexity of executing the test, so of generating the inputs, of verifying the outputs. And then it should be that there exists an implementation that succeeds in time. Okay, and the running time should scale favorably with the size of the test. So if the test has size k, maybe my running time should be linear in k, or maybe quadratic in k. Okay, so I'll just write here polynomial, some polynomial in k. Maybe k cubed is also okay. Okay, so as I go through my family of tests, as they get more and more complicated, my implementations also get more complicated, but their complexity doesn't scale doesn't increase too fast with the index of the set. And here it would be any classical, for soundness, any classical, let's say, I'll say algorithm or device that succeeds requires time, or in general resources, that scales much slower. Ideally, it would be exponential instead of polynomial. So I'll say, let's say 2 to the k, just not to write any constants, like something like that. Okay. So both concrete tests that have concrete completeness and soundness and asymptotic completeness and soundness are interesting for different reasons. I mean, in terms of the completeness, what I'd like to do ideally is have concrete completeness. This says that I can do the test right now. I can demonstrate my results, I can run the test, and I can see that the results pass. This say that by the time I get a large enough computer that absorbs the constants here, poly of k could be like 100 times k to the cube. And so even for k equals small, it's a little bit too big that I can afford right now. But soon, I'll be able to execute this test, and I'll have a favorable running time going forward. Soundness, ideally, you want a mixture of both of them. So this is both good because it's very concrete. It says, okay, like we just can't do it right now. But it doesn't say anything about tomorrow. Okay, so tomorrow someone could have a better idea and could find an algorithm that breaks your test. This could happen for factoring, for example. If you use factoring, currently we don't know how to factor, but maybe tomorrow someone has an idea. So it says, okay, factoring has concrete soundness, but asymptotic soundness, we can also argue about it, but we don't know for fact.
You have on the current limitation on resources. I cannot prove test what.
Oh no, because currently I mean currently. So like within a couple of days. It has to be commensurate with the time that's required to execute this. But let's say this took you a week. So here currently, or let's say a year, right, maximum. So with current resources, a year. Well, so the quantum device only is referred to in the completeness, and it depends on the size of the ideal device. I mean, it could still be that it's, yeah, it depends on the size of your device.
This does not refer, for example, to whether there is or there isn't fault-tolerant quantum computing.
No, so I mean, ideally, I'd like to lie here, and currently there's no fault-tolerant quantum computer, so I'd like a test that can be executed on a non-fault-tolerant quantum computer. Even here, I mean, this is very vague. The message is that I want the completeness statement to be the most immediate possible, so if it requires a fault-tolerant quantum computer, it's not that good. I'd prefer not to require a fault-tolerant quantum computer. I'd prefer to be using the computer that I have today. If I have something that's going to work in a couple of years, that's also not that bad. If it's 5 years, it's okay. If it requires fault tolerance, which is maybe 10 or 20 years, then it's just a little bit less interesting because I can't use it right now. I just want to make a comment. A comment is that part A says that, implies that there exists some behavior that succeeds in my test, okay? Test specifies inputs and outputs, and there is a way to succeed in that test because there is a quantum device that succeeds in it. Now, if you remember, I erased this, but the tests, they take this form, inputs and outputs. If there's a quantum device that generates valid outputs given the inputs, there also is a classical device that does this. It does it simply by simulating whatever is going on in here. Okay, so it might take a lot of time, but it's possible to do it. So what this implies is that in general, we're going to have to make assumptions on which to base the impossibility result, the impossibility statement that's made in the soundness. Okay, so the consequence in general, the consequence that's over there is that we need to make assumptions. And the goal in this game is to make assumptions that are the weakest possible and the most believable possible. In particular, we'd like to make assumptions that are independent from quantum computing, right? Ideally, things that have been well studied in other areas, that researchers in that other area believe, and that do not seem to be impacted by the existence or not of quantum computers. So 2 examples that we'll use later on are assumptions that come from complexity theory. So for example, the weakest thing that we could assume is that P is different from NP. Hopefully everyone is kind of able to parse that equation. But it basically means that there exist some problems that are hard to solve but easy to verify. Okay? And this is what we're trying to do. But we're trying to give a more refined version of this, right? Problems that are hard to solve classically can be solved quantumly and are easy to verify. So this kind of assumption seems like it's going in the right direction. So it's assumptions similar to that we'll make later on. And another kind of assumption would be from cryptography. So cryptography uses computational problems in order to base the security of communication systems. So these are things that are very extensively studied. Maybe we want to use post-quantum cryptography. So this is cryptography that's resistant to quantum attacks. Generally, these types of assumptions tend to be a bit stronger than these assumptions because these, not always, you could talk about one-way functions, but generally they refer to more structured problems, and the more structure a problem has, the more likely it is that in the future I'll be able to use that structure in order to break the problem. Here there's very little structure. There's more structure, but it'll also bias more, so we'll be using both kind of assumptions later on. Of some possible approaches to the problem that I'm describing. So I have a whole list, and maybe you'll have more suggestions. In each of the examples, I'm gonna discuss what is, first of all, the efficiency of the test itself. So test efficiency. Is this a test that's easy to run from the point of view of the party that's executing the test? So generating inputs, verifying outputs. Then there'll be the efficiency of the implementation. So this means, is this a test that I can run now, or hopefully in 10 years, or hopefully in 10 years or 20 years with the quantum device? And then the last column will be assumptions, which is what does the soundness statement rely on, right? I said there's gonna have to be some assumption because in principle, I can always fake the behavior that I'm testing for. So what kind of assumptions will I make? Okay, so one test that we've already, and the test is described here, so one test that we've already discussed is factoring. So what is this test? Okay, I described it. You generate 2 prime numbers, you multiply them, you give them as input, you get 2 numbers as output, and then you check that they're a factorization of what you entered. So test efficiency, this is very good. Generating prime numbers, multiplying numbers, etc. we can do so. This is extremely efficient to execute. Unfortunately, implementation efficiency, for all we know, you need to run Shor's algorithm, and for that, you probably need a fault-tolerant computer, or you need ridiculously low error rates. So this is, I don't know, I want to say, I mean, can't really do it now, right? Like maybe much later, but in terms of now, it's not so good. And assumptions, well, the assumption is that factoring is hard, classically. And you could say factoring is a problem that has a long history, so people have tried for a while to break factoring. There's a lot of money at stake. But still, it's a very structured problem, and there have been improvements over time in the speed of algorithms to factor. So I don't know how good that assumption is. I mean, it's decent right now, but it could break in the future. Okay, another test is a completely different regime, but if you just say, what's a test of quantumness, you could say, well, we know that it's a Bell test. Let's just do a Bell experiment. So So I won't describe what's a Bell experiment. Hopefully most people have an idea of what this would look like. In terms of running the test, well, that's extremely efficient. You just like choose some settings and compute the CHSH correlator or something like that. You can do that extremely quick. Implementation efficiency, well, let's do it like this. I mean, it's not that hard to realize. It's been realized since the 80s, except there's this spatial isolation assumption. So here you have a physical assumption, spatial isolation, and this kind of falls outside of my model, right? My model was I have one box and I want to test this box. Now you're telling me you need two boxes and they need to be space-time isolated, and how do I check that? I need to run my test fast. If I need to run my test so fast, the efficiency kind of goes down. So you could argue about this for a while, but I'll just say that it's outside of my framework, and so we don't discuss it anymore.
Thomas?
Yeah.
Regarding this strict requirement of isolation, they were important in the foundation of quantum mechanics.
Yeah.
But in the context of studying a device, are they really essential? Do you think of
no, but I am testing the foundations of quantum mechanics here. We are really putting in question whether it is possible to implement a quantum device that realizes a task that cannot be realized classically. So it's really a foundational question rather than a purely algorithmic question. So in that sense, it's appropriate.
Maybe I'm confusing contexts, but discussions where the spatial isolation in the present can be replaced with cryptography and the game will essentially one part replace itself. Can you draw a parallel and get rid of?
Well, that's a much more advanced topic, so I'll get to that later. So then something else that's been discussed here are optimization algorithms or quantum algorithms for combinatorial optimization. For example, the QAOA that Eddie has been discussing, or more generally, like a variational quantum eigensolvers. Okay, so QAOA has been discussed, so I don't need to say what this is. Okay, implementation efficiency, this is kind of good. I'll put one tick because you can do small experiments based on QAOA. Test efficiency, well, it depends what the test is. I haven't specified it, but for example, to connect to Eddie's lecture, you would generate a large graph and run QAOA in order to find a big cut in that graph. So generating a large graph, verifying the size of a cut, this is pretty easy. So from a point of view of verification, it's very efficient. Now assumptions, and that's where it gets a little bit fuzzy. The problem, as far as I understand, is that there is no clear family of instances of a combinatorial optimization problem for which we have a convincing theoretical evidence that the QAOA is going to provide results that beat the best classical algorithms. Okay, there's sequences of papers that fight each other, and Eddie very described this very well. But this is kind of an ongoing race, and the theoretical basis is not clear. So I would say inconclusive. We don't really know at the moment. Continuing kind of in this line of work, I could talk about quantum simulation. Quantum simulation is one of the avenues for demonstrating a quantum advantage in the near term. So how well does it fare with respect to my criteria? So it's also mildly efficient. I mean, people do implement analog quantum simulators for certain kinds of systems. The problem here, I would say, is that there's no test. What is the test? The test is, can you please simulate that system and give me the results? But there's not something that will accept or reject the results a priori. You want to see some kind of graph, some signature of something, but there's also no arguments for why it would be hard to produce specifically that signature. It's kind of like it's very fuzzy. So I'll write murky. Or okay, let's say fuzzy. Murky is a bit fuzzy. Test efficiency, I mean, here I'll put a question mark because I kind of want to say that there's not even a well-defined test. Like, what's the test? Maybe someone could come up with a test such that completeness is achieved using quantum simulation, but I don't know of any such test at the moment. Okay, I have two more lines, which are the two lines that I want to get into more detail in. So random circuit sampling and the cryptographic tests. Before I go there, does anyone have some other ideas?
What about all of the questions?
Such as?
search Jota?
Aha. So I'll actually talk about this in the last lecture a little bit, but the problem of that is that I can't execute the test. Like oracle separations, they make the assumption that there's a certain function, and that function can only be accessed by everyone, by the quantum machine, the classical machine, in a very specific way. You can only ask questions, you give an x, and you get back f of x. But that's a very theoretical model. In practice, if I want to execute the test, I need to say what the function is. I need to give you code. I need to say, okay, the function f of x is x squared, or x plus 1, or something like this. And the problem is that this is why these are black box separations, or oracle separations. We don't know of any f for which, if we select that f, the problem is going to remain classically hard. For all we can think of, any f that we think, any concrete function f, then there's a classical algorithm that solves the Giosa or Simon for that f. And so we just don't know how to instantiate the test. It's only purely theoretical. In principle, in this oracle world, there exists a function, but we don't know what it is, so we can't run it. Okay, we can talk about it more later if you're. Other suggestions? Huh? Boson sampling. Okay, so let's talk about that. So then there's approaches based on sampling. So maybe I'll just call it sampling. An example is boson sampling, for those of you who've heard. Boson sampling. Another example is random circuit sampling, so random circuit sampling, which we'll talk about much more soon, and there's a few related proposals. Loosely speaking, in these proposals, the input is a random circuit from some family of circuits, so it could be linear optics, could be a random circuit, could be a random QAOA circuit also. So a circuit from that family, you put that as input, and then you ask the device to simply execute the circuit, measure the output, and return that. And you do this many times, and you collect statistics, and you try to argue that the statistics you collected are a signature of the fact that the device has indeed implemented the correct quantum circuit. So these have one major advantage, which is that they can be implemented today. That's what the Google experiment and also experiments based on boson sampling demonstrate. They also have fairly solid theoretical evidence for them. This evidence is based on complexity theory, and I'll describe that in more detail. One of the main drawbacks that they have is that the test efficiency is very low. So generating inputs, generating these random circuits, that's easy. The problem is verifying the outputs. In general, you'll get strings that are supposed to have been obtained by sampling from the circuit, and you don't really know what to do with them. And I'll describe that a little bit later. There's statistical tests that you can perform, but for the test to be efficient, you need to make shortcuts, and these shortcuts open avenues for classical algorithms to spoof your test. And so there's a little bit of a very thin line that you're walking there, and I'll discuss that after. The last approach that I want to discuss is based on interactive tests. And I'll describe that in the third lecture, maybe a little bit before, so I don't want to describe it now. It's related to your question. But just to give it away, these have one major advantage is that they're very efficient to execute. In terms of assumptions, it's also fairly sound. They're cryptographic assumptions. But in terms of implementation efficiency, we're not quite there yet. I mean, this is kind of something like this. It's actually not quite clear at the moment if these can be executed on a non-fault tolerant computer. I would say that's an open question. You can do proof of principle demonstrations, but they're very small scale, so it's not quite there yet. Okay. It's actually an open problem. The major open problem that will be left over at the end of my lectures is to develop a series of tests that combines this box and that box. And currently we don't know this, which means that at least as far as I'm concerned, it's currently unknown how one could even go about performing a convincing demonstration of quantum advantage. So that, I mean, the problem Grover is the separation is in the black box model. So again, there is no concrete function for which you would want to perform search, for which we know that for that function, the best classical algorithm has to search through everything, and there's a quantum algorithm. So that's one inconvenient. It's a black box. It's an oracle separation. The other is that the separation is kind of small between n and root n. And so in order for you to really see the difference, you need n to be very large. But then that means that the quantum algorithm also needs to be very large. And so, yeah, you run into a problem.
What about, for example, deciding if the quantum circuit is the identity?
Deciding if a quantum circuit is the identity. So the input would be a quantum circuit, and the output would be it's the identity or not. So as far as I know, that problem is not even in BQP. It's I think QIP2, it's like, yeah, the problem is that you give as input to the device the description of a quantum circuit, and that circuit could resolve to the identity circuit or not. Like there could be a ton of cancellations or not, and the device has to decide to answer. So the way the quantum device would go about it is that it would just run the circuit on many random inputs, and if it always sees the same output as input, it'll say, okay, look, like this was the identity. Yeah, okay, on a particular string. So if the circuit is the identity in a particular string, I think that's equivalent if you allow all circuits, because you can just, I think this will be equivalent. So I think that problem is too hard for even a quantum computer. Because the test that we just described, if the is the identity in a particular string. No, but that's the same as deciding, that's BQP complete, right? So, I mean, you could try to do this for BQP complete problems, but they're not, you don't have this. If you want this, you're going to need to do it for very small circuits, and for these small circuits in general, there'll be a shortcut. You'd have to say very precisely how do you select your circuits, and that that's kind of one thing that these guys are doing. They're saying exactly what kind of circuits might give you hardness. Yeah. So that's that's very convincing for in a particular. So let me get to the motivations. And maybe some of these motivations will say why the Bell test I'm not considering, even though it's a very good test of quantumness. So here are my motivations. So the first two are related. The first one is that if we look ahead, of course, the most interesting thing to do is not to develop test of quantumness of quantum advantage. The most interesting to do is to solve some problems of practical interest. And I think the day that we manage to do that using quantum computers, these questions will kind of disappear. I mean, they'll become just a playground for theorists, but experimentally they won't be that interesting. Unfortunately, if you draw the axis of time, I don't know, everyone's best guess is a bit different, but for me, I'll put it at 20 years, let's say. So 20 years, we have a fault-tolerant quantum computer that's large enough to factor and also solve many simulation problems, and then this is done, right? Okay, but what happens, in that time range? So maybe much before, let's say 10 years, we have computers that solve problems of practical interest. So for me, this is something like you need maybe 10 to the 3 qubits, okay, to arrive at a size that's interesting. If you do quantum simulation, there's always some overhead. And the problem is that the error per qubit will have to be pretty small. So it'll be something like 10 to the minus, less than that for sure, error per operation. Okay, because if you want to run a circuit on that many qubits and roughly that many gates, we should actually, probably be lower. So we're definitely not there. So maybe 10 years. I mean, I don't know. I'm not an experimentalist. We can argue about this in the corridors. And so the question is there anything that you can say here that will allow you to, you want to be able to benchmark the computers, and you also want to be able to determine that they're accomplishing tasks that have no classical analog. And so the goal is to have some tests that we can use now and in 1 year and in 5 years up to 10 years, maybe all the way up to the 20 years, at which point they won't be that useful anymore. Motivation B is really a fundamental motivation. So this is the one that the Bell test doesn't fall in. So there's kind of like used to be a dogma, but no longer in computer science since the 60s, which is that the Turing machine, which is the abstract theoretical model for the classical computer, captures everything that can be computed in the real world. As far as we know, this is still the case, but there's a bit of a strengthening of the thesis, which is the extended Church-Turing thesis, which says that any process that can be implemented efficiently in the real world can also be simulated efficiently by a Turing machine. And when quantum computing was discovered in the 80s and Shor's algorithm, that challenged this thesis. It said, no, look, here's a process. I can describe it. It seems to be resistant to errors. And it's solving a problem that we don't know how to solve efficiently using a Turing machine. So that kind of like threw computer science upside down. But it was completely theoretical. So, okay, like maybe. Now we're arriving at the point where maybe it's no longer theoretical. Maybe we can demonstrate this. And for many computer scientists, it's very exciting. And we'd like to get there as soon as possible. So that's the second motivation. The third motivation is, okay, I don't know if you can see the bottom because of the board. Okay, is that even though I claimed as my primary goal to just develop tests of quantumness that test only this, that differentiate quantum behavior, specific quantum behavior from any classical behavior, ideally I'd like to develop this series of tests in a way that can be used for applications. For example, going back to the Bell test, this is not only useful for foundations, but you can use it for cryptography, and that's a big plus of it. So maybe some of the tests that we develop here could also be used for cryptography, and that would ensure that they live beyond those 20 years. Maybe they can be used for other applications where privacy or security is important. Applications where you don't trust the devices that you're interacting with, such as delegated quantum computation, so quantum computing in the cloud. So what's our strategy going to be? And we'll apply this strategy in two specific cases. The first step is going to find some quantum phenomenon that seems to provide an advantage for quantum systems. And the second step will be to develop a test or a series of tests that leverages that quantum advantage. So three examples. The first one I'm not going to talk about, but is entanglement and non-locality. This is a quantum phenomenon, and the Bell test is a way to evidence that phenomenon, verify it. Second phenomenon would be interference. So interference is sometimes placed at the heart of quantum advantage for algorithms, and arguably this is what the quantum sampling algorithms make use of, and I'll go into this in much more detail. And the last phenomenon is the uncertainty principle or complementarity. So it's the idea that in quantum mechanics there are families of measurements that can be performed separately but cannot be performed jointly. This seems like a drawback in a way, but actually we'll see how to use that in order to realize a quantum advantage in an interactive setting. So before I go into the two specific directions that I chose, I want to emphasize that I chose them partially because they're the most prominent ones, but not because I think that you should know all the intricacies of what is random circuit sampling and what's the computational, the complexity theoretic basis for it, or what are these interactive tests and what are the basis for it. But what I want is to give you a flavor of the kind of reasoning that's applied in this area so that later on, when you think about this problem, whether something is generally quantum and whether it fits in the framework, then you have tools that enable you to formulate the problem, to understand whether it fits like the kind of specifications that are described, and if you actually want to argue that the task that you're considering just demonstrate a quantum advantage, then you have some sense of the tools that can be used in order to show that. Questions? I think I started a bit late, right? So I can take like 5 minutes to start talking about random circuit sampling, and then but stop, like still ahead enough that there's time for questions on this. Or if there's questions on this already, we can just take them and I'll restart tomorrow. Yeah?
When you went through all the different methods, you said about quantum simulations, that there's no efficient test. You mean that whenever a very large quantum system, I can't numerically verify it?
Yeah, so kind of. Yes, the point is that there's no, there's two ways you can go about this. You can take a system that you don't know how to analyze classically, and then you can say, okay, I'm going to run a simulation that simulates that system, and then I'll make some measurements of certain observables and plot a graph of the results and observe that I have a phase transition kind of like where maybe some model expected it to see. Okay, but that's a posteriori verification. So you're not specifying a test. You have to say what the test is ahead of time. The test has to say what system you're interested in. I mean, that's totally fine. You have that in mind. But it has to say what outputs are going to be accepted and what outputs are not accepted. Okay? So let's say you tell me, well, you know, I accept a graph that looks like this. Okay? Because this like the phase transition that you expect. Then I'll come and I'll say, well, okay, run your test on me. And then you're going to do it, and then I'll go in my corner and I'll draw the graph, and then I'll give it to you, and you'll be like, oh, okay, but you cheated. But that, you know, so the problem is that they tend to make you bake in a lot of beliefs about what is going on in order to, there's no verification of the results per se. You see what you expected to see, and because you know the system and you kind of know what went on in there, it helps you, raise your confidence in the fact that what's going on is good, but you don't have a way to verify it. That's one thing. The other thing that you said is also correct, is that in general, quantum simulation is trying to make predictions for the behavior of certain systems that actually are unknown. I mean, we don't have other way to make these predictions, but then in that case, you also don't really have a way to verify them. You know, you can do some rule of thumb kind of tests, but these are not, they're not foolproof. Okay, so let's talk after. Okay.
Can you simulate like real life, and then you go to the lab and you do the mathematical?
So what do you mean a bit more specifically? So you'd have to say what are the inputs and what is the test?
I have some physical system in my lab.
Okay.
And I ask you to simulate it and give me some values of.
Okay.
After that, I measure them in the lab and I compare.
You compare. Okay. So you could do that, but it's kind of like circular because, okay, you're kind of asking, can you please reproduce my system? And you're saying, okay, but you need to have a belief. You need to have a belief, which is that the behavior of your system in your lab, the one that you're asking me to simulate, whatever results it's producing, there's no classical way of producing them. I can't run, DMRG is not going to work, some other ansatz is not going to work. You need to be sure of that. And if you tell me that you're sure of it, that's still not enough for me. I'd like to have some consequences from it. Like, okay, suppose that someone could spoof your test. Then what? And I'd like you to be able to tell me, well, then this widely believed conjecture that's completely independent of my system, completely independent of quantum mechanics is going to be falsified. And then I'll be like, okay, now I want to try to falsify it. So it really depends what you're interested in, right? I said from the start that I'm taking a very adversarial point of view. I'm not giving any trust in your system, and I'm really going to try to break whatever test you come up with the hardest I can.
I don't think it's a big test because a classical person could be in lab and do the experiment.
Right. So I mean, well, not maybe his lab is very advanced. I don't know, and so maybe it's hard to build this in lab. But yeah. So ideally, that's what's hard about this verification. You need a shortcut, right? Somehow, this is why assumptions such as P different from NP are relevant, because you need a task that is hard classically to execute, but if someone manages to generate correct results, using a quantum computer, it's going to be easy to verify. And that's not so obvious to find such examples of this kind of problems. So this is a proposal for a test of quantumness that arose from a research group at Google, led by Sergio Borxo and others. And after the experiment was proposed, it was realized by John Martinez and his group at Google. The arguments for why this is a test that's hard for soundness, why it's a test that's hard to spoof, classically, these arguments go back to before. They go back to Arnson and Arkhipov, who introduced boson sampling, and they're really the ones who traced the route that I'm going to describe in the next lecture. And then there's some other reference. I have some references at the end. Let me tell you what the proposal is. So the concrete version of the test is that you fix a certain number of qubits. In the case of the Google experiment, there's 53. And you also fix an architecture. The architecture just says where gates go and how many layers of them you have. So in the case of their experiment, the architecture is 2D. So the gates are nearest neighbor on the 2D architecture, and there's 20 layers of gates. So this fixes the architecture, but it doesn't fix what the gates are. Okay, these are just boxes, but I haven't written anything inside them. So what's the test itself? So you're going to repeat, a certain number of times. So I put here the data from the first experiment, their experiment. So you repeat a certain number of times. Here it was 10 times. So you're going to choose a random circuit by selecting uniformly at random the gates inside each box. So where the boxes are, this is fixed, but then you get to decide, is this a C0 gate? Is this just 2x gates? Is this, I don't know, some other kind of gate? And you're supposed to select those uniformly at random according to the Haar measure on two-qubit gates. So you choose this circuit, and then you're going to repeat the experiment a very large number of times. So here, like 30 million times. What you do is that you initialize the circuit always in the same state, the old 0 state. You execute the circuit, and then you measure to obtain the outputs. You do this for the same circuit 30 million times. And then you have all this data that's been generated, and then you compute a score from the data. And I'll get into what the score is more or less next time, but it's some function of the circuit and the data that's been generated that's kind of that's supposed to measure the statistical correlation between the outputs that you've generated and the actual output distribution of the circuit. The reason that this is tricky is that this is a circuit on 53 qubits. Okay, so when you measure 53 qubits, and you get a 53-bit string. So there's 2 to the 53 possibilities. 2 to the 53 is much, much bigger than 30 million. So all these y's that you get, they're all different. And so you have to come up with, okay, what kind of y's are good and what kind of y's are not. And so we'll discuss that next time. I think I'll just stop here so we have a few minutes before or questions. So let me stop, and then the next 2 lectures, one lecture will be on random circuit sampling, and the other will be on the cryptographic. Clifford gates is not a good test, but I didn't write Clifford. I wrote, choose circuit C by selecting each unitary gate uniformly at random. If you select a 2-qubit gate uniformly at random, it's not going to be a Clifford gate.
Because you said the C0 and then X.
Yeah, okay, this is what came to my mind, because I don't know how to describe, but it's going to be something with some coefficients that, no, it's not going to be a C0. You have to choose it at random.
But nobody knows how to make magic states, so how could they make?
So I don't know exactly what Google did, but I think that's not true. You can synthesize approximately the gates. So you're going to choose a 2-qubit gates that has, they don't know how to do magic states with very high fidelity, but this is not a high fidelity experiment. So you select a gate, you select all the coefficients, and then you run the classical algorithm that's going to depend on your hardware, and that's going to say, okay, to synthesize this gate, you have to do these single qubit rotations and a few C0s and some single qubit rotations. The single qubit rotations, they're not Clifford. And maybe there's a non-Clifford gate that the device can implement. I don't know what their architecture does, but it's going to say that. And so in practice, each 2-qubit gate is going to be realized using more gates. Ideally, I think what they did there is that they just selected gates from a family of random gates that they can implement. You have a little bit of freedom there, but not Clifford's. Yeah, not Clifford's.
Does this test fail soundness?
So why? So failing soundness means that there would exist a classical device that is able to pass the test. Then we have to talk about concrete or asymptotic, but no. So I'll try to describe in the lecture why there's convincing evidence that a variant of this test could not be passed by a classical device. In fact, as maybe many of you know, this specific test can be passed by a classical device. So that experiment demonstrated exactly what I referred to as a completeness and concrete soundness. We could do the experiment in a day or a week, and the day or week that we did the experiment, we didn't really know how to generate data that would pass the same test efficiently. And Google made estimates, and they said it'll take like 10,000 years or something, so we're safe. But then, of course, people looked at, okay, but specifically, what is your test? And show it to me, and okay, and let me try to take shortcuts, and what's your noise, and this. And then there was kind of a race for maybe 3-4 years, and now people are able to succeed in this specific test, in an hour or two using like a reasonable computer. So it has advantage for like a couple of years or something, which is better than anyone else has done. So.
Is there any evidence to assume that without photon can hear?
That's a very good question. I mean, the question was, to use your words, is there any reason to assume that without fault tolerance, anything like this can be done, basically? So, I mean, I said it's an open question. So I'm not assuming it, I'm trying to solve it. I or researchers in this area are trying to come up with tests that have some form of reasonably concrete efficiency, in particular would not require fault tolerance, and have as strong possible concrete and asymptotic soundness. And is it possible or not? I don't know. It's a good question. We're trying. No, well, I'll try to give some intuition for that particular proposal. No, the intuition is that seems hard. Quantum simulation, I try to like shoot it down, but it doesn't give it because it doesn't give a test, but it gives some of the intuition. It just seems to be the case in practice that there's many things that people are able to do in the lab or have a strong feeling that they'll be able to do in the next 5 years that really will beat the best numerical methods by orders of magnitude, right? So, and without any fault tolerance. These are like quantum simulation or even some experiments based on VQE or things like this that not now, but maybe in 5 or 10 years would pan out before fault tolerance. And so this gives intuition, but we're trying to give like a basis for that intuition.
Can you repeat? I think you said it, but I didn't catch it. Can you repeat? How do I verify that the result of boson sampling are not just garbage?
No, I didn't say it. It's very delicate. I'll say this next time. It's extremely delicate. What I said is that it's going to require a lot of time. I mean, it's okay. I'll say it again next time. But since it's on my slide, this is not what they did. This XED is a specific function that you compute, and I won't even say what it is, but I'll give a hint. But ideally, you'd want to estimate the total variation distance, if you know what it is, the statistical distance between the correct output distribution. The correct output distribution, if you have lots of time, you can compute it. For every y, you can compute the probability that this circuit returns y. Well, it's going to take a lot of time, but if you have a lot of time, you can just do a simulation, exponential time simulation. And
if I know the answer, why can't I simulate classically?
Yeah, so I mean, I said it. That's the problem with this test. So this is why, no, but this is why there's a whole history, but this is why they took a shortcut. So this XEB is something that's supposed to be a little bit quicker to check than what I just said. But then the problem is that to make it easier to check, you take a shortcut, and this shortcut enables people to fake your test. And it is the main downside of this approach, that verification is not efficient. The main upside is that you can do the experiment. And so you're trading off what you can at the moment. Good.